So good evening and welcome to the Darwin College Lectures, which, as you well know, this year have the overall theme of foresight. And it's welcome to everybody here in the Lady Mitchell Hall and everyone who watches online. The lectures are freely available through the university's streaming media service. If you want to look at anything again, just go to the Darwin College website and follow the links. So far in this series, our speakers have covered foresight in ancient civilizations, in journalism, and in science fiction. And tonight, we turn to what some might regard as the hard core of foresight, and, if you will, prediction, the scientific method. But before we do that, it's perhaps worth remembering, especially as we're in the Lent term here, that we can still predict Easter by the astronomy of Claudius Ptolemy. So perhaps arguably the most successful scientific theory of all time. Indeed, the maths may be more complex if the sun goes around the Earth, but is it invalid? Now, with due homage to the long line of thought from Socrates to Karl Popper, I doubt if many of us understand how our science works. I, for one, don't, and politicians certainly don't. The concepts of curiosity or blue skies science can be completely mysterious to those who fund us. Creative underemployment, serendipity, unexpected outcomes, or even mathematicians working at 3 a.m. clad only in their dirty socks are an anathema to those who insist on timesheets. Now, J.J. Thomson certainly didn't set out to discover the electron, and indeed when he had, it wasn't thought to be particularly useful. Yet our society here now is impossible without our understanding of electrons. Do we judge by impact? Now, impact is a particularly high blood pressure word in the UK academic community at the moment. Before we're funded, we have to say what we're going to discover, and then afterwards we've got to give all the evidence. Where's the place for luck? Maybe Rutherford said he made the wave. Luck smiles on those who are ready to see her, and discovery becomes inevitable. But today there's a terrible suspicion in our management of science that the good is just driving out the best. Now, it gives me particular pleasure this evening to welcome our speaker, Professor Ha-Seok Chang, Professor of History and Philosophy of Science here at Cambridge. Ha-Seok studied for his undergraduate degree at the California Institute of Technology, moved a short distance to do his PhD at Stanford, and then crossed the Atlantic to take up a position at UCL, where he has been for 15 years. And he moved to Cambridge, I think, in 2010. Ha-Seok is the president of the British Society for the History of Science. He's obviously got numerous publications, including his most recent book, Is Water H2O? Evidence, Pluralism and Realism. Ha-Seok, welcome, and we look forward to your views.
Thank you. Well, thank you very much, Professor Fowler, Mary, for that generous introduction. I'm very, very pleased to be here. Can everyone hear me okay? Thank you. I'd also like to thank several people before I begin. First of all, Dr. David Feller, who had the crazy idea to invite me to give a talk in this series. Also Professor Sherman, Professor Brown, and everybody else involved in organizing this wonderful lecture series. And thank you all for turning up. Now, my brief today is to discuss foresight in relation to science. I don't think it's difficult to justify the inclusion of this topic in this year's series. Of all systems of practices and beliefs that humans have created over the centuries, modern science is widely regarded as the one with the best ever claim to foresight. Scientists have used their theoretical insights to make impressive predictions of future events, which have contributed enormously to the prestige and authority of science. If foresight was always equated with wisdom, then it is no surprise that scientists gain their status as wise men. I wonder if Jeffrey Lloyd spoke about that issue in his opening lecture of this year. I do apologize for not having been able to attend the previous lectures of this year's series because I am actually on leave this term and not in Cambridge, except right now. It's 9 hours later where I have been in Korea, so if I start falling asleep, please pardon me. Initial successes of science's foresight often involved predicting when certain striking phenomena would occur, demonstrating the understanding of natural patterns that govern phenomena that had seemed mysterious and supernatural before. The predictions of lunar and solar eclipses are salient examples. And there's also the famous case of Edmund Halley's prediction about the return of the comet named after him now. More mundane yet highly significant successes also followed, such as improved weather forecasting and medical prognosis. The foresight displayed by science also went well beyond pattern recognition. As the physical sciences matured, previously unforeseen kinds of entities were predicted by theory, and many such predictions were gloriously vindicated. The prediction of the existence of new planets, particularly Neptune, was a striking enough success. Then came more bizarre and wonderful successes, such as the discovery of new chemical elements predicted by Dmitri Mendelev's periodic table, the realization of electromagnetic waves predicted by James Clerk Maxwell's electrodynamics, and the detection of a whole series of new elementary particles predicted by theories of modern physics, the latest instance of which is the famous Higgs boson. Not only new entities, but unexpected behavior of familiar entities predicted under particular conditions specified by theories also made great impressions on people's minds. Einstein's prediction of the bending of starlight passing by the sun literally made news headlines around the world in 1919. Physicists became fearsome sages of the post-war world by predicting the possibility of the atomic bomb and then delivering the actual thing according to plan. Now, I could go on and spell out the various kinds and instances of foresight displayed by science and probably be able to make a relatively informative and amusing lecture out of that. But my aim is more critical. And you didn't come here to listen to stuff that you can easily look up on the internet. Accepting that modern science has displayed an impressive degree of foresight about nature, I want to ask what the precise significance of predictive success is within the context of the scientific method. That question will occupy roughly the first half of the rest of my lecture. After that, I'll raise a slightly different question about foresight relating to science, namely, can we foretell the future of science itself? I will answer that question mostly in the negative, and close by discussing the implications of that answer. So here is the list of major questions that I propose to deal with today. The first one I've already answered with a fairly simple yes. At least a qualified yes, meaning much better than any other system of knowledge or belief known to humanity. That may not be saying much, but it is something. I now move on to the second question. Many philosophers and scientists have especially valued the ability of science to make novel predictions of stuff that we had not known or seen before. sometimes to the point of regarding it as the defining characteristic of science. This view, which I will call predictionism, has a long history, but in modern times it is most clearly revealed in the philosophy of Karl Popper and Imre Lakatos. In Popper's falsificationist methodology of science, only failed attempts to refute a theory can count as corroborating evidence for it. And the more severe the test, the higher the evidential value. The basic predictionist intuition is that anyone can make up a theory to fit known data, but the true test of a theory is correctly predicting something unknown. The true scientific attitude, according to Popper and other predictionists, is the willingness to give up theories that make predictions that turn out to be false. And the predictions are no good unless they take real risks. Vague predictions that are compatible with anything that happens are a sure sign of pseudoscience for Popper, as in, say, today's newspaper astrology columns, which will tell you that, say, if you're Aries, which I am, you may find love in an unexpected place today, etc. Here's an actual example from a while back. This you probably didn't expect to see today, but here, if you're Aquarius, for that day, it says, no matter how convinced others are that they know the facts, with Mercury retrograde until next Thursday, they could be making mistakes. Just in case that was too definite, the horoscope goes on. What's tricky, however, is that until you investigate matters more thoroughly, you cannot say exactly where or in what way their facts are incorrect. Precisely the kind of thing Popper was objecting to. But for the young Popper, spending his formative student years in the desperate ferment of Vienna in the aftermath of defeat in the First World War, battling pseudoscience was very serious business. He railed against the Marxists who had no trouble explaining every occurrence in society according to their grand theory of history, and then twisted their theory to accommodate happenings that went against their own predictions. This, Popper thought, and Lakatos thought, was exactly what they had done in the face of the first communist revolution, which took place in agrarian Russia, not in a place that had reached the height of capitalist development as Marxist theory had predicted. Popper also attacked in the same vein the popular psychological theories arising in Vienna at the time, namely Sigmund Freud's psychoanalysis and Alfred Adler's so-called individual psychology. Popper actually worked for a time with Adler, assisting him in the social guidance clinics that Adler had established for working-class children and youth. Popper was at once impressed and disturbed by Adler's ability to interpret all psychological phenomena according to his own theory, which emphasized things like the individual's desire for superiority and at the same time the individual being hampered by an inferiority complex. That's Adler's term. Popper reports one particular personal experience which philosophers of science amongst you will be very familiar with. I quote from his recollection. Popper says, once in 1919, I reported to Adler a case which to me did not seem particularly Adlerian, but which he found no difficulty in analyzing in terms of his theory of inferiority feelings, although he had not even seen the child. Slightly shocked, I asked him how he could be so sure. Because of my 1,000-fold experience, he replied, whereupon I could not help saying, and with this new case, I suppose your experience has become 1,001-fold. What I had in mind was that his previous observations may not have been much sounder than this new one, that each in its turn had been interpreted in the light of previous experience, and at the time counted as additional confirmation. What, I asked myself, did it confirm? No more than that a case could be interpreted in the light of this theory. So that's Popper's recollections. It's interesting to remember that Popper was born in 1902. So at best, he was 17 years old when this happened, and that's roughly the picture of him at that age. So I don't know how heroic he really was going up against the great Adler, but that's what it tells you later in life. The great contrast to all this for Popper was Albert Einstein's general theory of relativity. 1919 was an important year on this side too, as that was when the British astronomer Arthur Eddington led the expedition to observe a solar eclipse to test one of the striking predictions of Einstein's theory. Many of you will already be familiar with this story, but let me just explain the basic idea for those of you who aren't. So Einstein's theory predicts that space-time around a massive object like the sun curves around in this rather poor presentation. It's just seen as a dip. And when a beam of light passes by that heavy object, going through that deformed area of space-time, it bends. So our eye, an optical instrument, would naturally assume that light had come straight from its source. Therefore, the apparent observed location of the object is different from the real location, which is shown on the left side of that picture. I hope that's clear enough. So if you could look at the apparent locations of the stars right around the sun, and then compare those locations with what you would see at night when those stars are not in the pattern of the sun, you would see a difference. That's Einstein's prediction, which you could confirm by looking at stars around the sun. Well, there's one problem with that, which is you can't see anything around the sun because the sun's too bright, which is why you need a total eclipse of the sun. So that was Eddington's plan. He said, we will go down to where there's an eclipse. We will take pictures of the locations of the stars right around the sun, and then we will compare those pictures with pictures taken at night. And here you see, on the lower left, you see an instance of those pictures. That shows you what you see when you superimpose two plates, right? One taken around the eclipse, one taken at night, and you can see basically how there are slight deviations in the dark spots which represent the stars. So Popper thought Einstein's theory stuck his neck out by making a very apparently implausible prediction that light would bend. And the neck that Einstein's theory stuck out was mercifully not chopped off. Sticking the neck out was one of Popper's own favorite metaphors. So this was the best of science, in his view. Pseudoscience busies itself with making sense of already known facts. Real science is the business of foresight, exploring and expanding the frontiers of knowledge by foretelling what we don't know yet. Modern science has demonstrated great foresight, and this is what makes it so great. Now, Popper's predictionism was elaborated and refined in instructive ways by the Hungarian philosopher Imre Lakatos, who also taught at the LSE. Now, I shall be brief about Lakatos because I don't have enough time, but if you are interested, I can elaborate on that if you would email me with a question. There is my email address on the first and last slide showing the title of this talk. Let me just very briefly say about Lakatos that he took a slightly modified stance compared to Popper, to the young Popper, and Lakatos always maintained that he was only extracting the mature Popper's best insights, and Popper didn't quite agree, and he claimed that Lakatos never understood him properly, but let me not bore you with that debate. Lakatos's major modification, as I see it, is that he allowed that it is perfectly fine for a scientific theory to make allowances for itself. So rather than scientists immediately discarding a favorite theory just because it seems to be refuted by some evidence, scientists are allowed by the scientific method to make slight modifications in their theoretical beliefs in order to save the theory from refutation. And Lakatos said it was okay to do that as long as in the course of protecting your favorite theory, you also made these novel predictions as a side effect. So the best example to illustrate that idea of Lakatos is the discovery of the planet Neptune, which I briefly mentioned before. So the brief history of that is that when the planet Uranus was discovered by William Herschel, the observational astronomers noticed that the orbit of Uranus didn't go exactly as predicted by Newton's theory of mechanics and gravitation. Now, instead of discarding on the basis of that one anomaly what was the best ever scientific theory in the history of humankind, the astronomers said, there must be something else wrong here. So they said, what if we can change some other auxiliary assumptions that go along with Newtonian physics? For example, they said, what if there's actually another planet beyond the orbit of Uranus, which would be disturbing the orbit of Uranus with its own little gravitational field? And they were able to predict, on the basis of the Newtonian theory, exactly where that extra planet ought to be and what its mass would be and so on. And then when they looked at the predicted place, they did find Neptune. Now, that's the Hollywood version of that story, but it illustrates the point that Lakatos is trying to make. It's okay to make what seems to be an ad hoc hypothesis as long as you are actually making novel predictions on the side. So as I mentioned, this kind of insight about the value of novel predictions was not new to Lakatos or even to Popper. I just give you one instance, a very old predecessor, René Descartes, who said, we know that our hypotheses are correct, I quote, only when we see that we can explain in terms of them not merely the effects we had originally in mind, but also all other phenomena of which we did not previously think. So after hearing Popper and Lakatos with echoes of Descartes, one may become convinced of predictionism. But as it usually goes in philosophy, there is an opposing position that is equally convincing. This is a position that I call logicism. The basic intuition for which is that confirmation of a theory is a matter of logical relationship between hypothesis and evidence. The temporal order in which they are arrived at is irrelevant. Contemporary philosopher of science Laura Snyder expresses what she calls the objective concept of evidence in the following way. She says, I quote, whether E is evidence for H does not depend upon anyone's beliefs or knowledge about E, H, or anything else. Hence, if some E is evidence for H, it is so regardless of what any person knows or believes. End of quote. She's putting that in a deliberately abstract, formalistic way to make the point that this is a matter of a formal relationship. So it should not matter whether scientists first formulated the hypothesis and then found the evidence, or vice versa. All that matters is that H predicts E, predicts in the logical sense, meaning that we can deduce E from H. Snyder's concluding words, evidence is evidence is evidence. Like predictionism, logicism has a long and distinguished history. John Stuart Mill's comments might well have been directed at Popper almost a century later. Mill said, such novel predictions and their fulfillment are indeed well calculated to impress the uninformed. But it is strange that any considerable stress should be laid upon such a coincidence by persons of scientific attainment. The exact same point was voiced by the Cambridge economist John Maynard Keynes, who said, the peculiar value of novel prediction is altogether imaginary. The question as to whether a particular hypothesis happens to be produced before or after examination of its instances is quite irrelevant. Now, I think it's quite difficult to argue against the general point voiced by Snyder, Mill, and Keynes. There are also some specific circumstances gathered from the history of science that add to the skepticism regarding predictionism. For example, there are perfectly respectable sciences without many testable novel predictions. Let's say paleontology, evolutionary biology, old-style geology, cosmology, etc. And there is apparent evidential value of so-called used evidence, the evidence that you did use to come up with your theory in the first place. So we would not deny that Galileo's law and Kepler's laws, etc., still serve as valuable evidence for Newtonian gravitation, even though we know that Newton actually specifically used those regularities to figure out his inverse square law. So this debate has the shape of a classic philosophical dilemma. Both sides seem right, but they cannot be reconciled with each other. And I'm going to make things a bit worse for you. There's a surprising third view from the historian Stephen Brush, who has argued that the accommodation of previously known facts can be actually more convincing evidence for theory than the prediction of new facts. Here's what Brush says. A successful explanation of a fact that other theories have already failed to explain satisfactorily, for example, the Mercury perihelion, is more convincing than the prediction of a new fact, at least until competing theories have had a chance and failed to explain it. So here he's drawing a contrast between the light bending case that I spoke about earlier and another another achievement of the general theory of relativity. So Brush is saying, yes, light bending, nice. Einstein predicted it. It happens. But how do we know whether there are other theories which would also predict it? Maybe even more precisely. We just don't know yet. We haven't had time. Well, we have now had time, but in 1919, we had not had time to think about that carefully. In contrast, the perihelion case he's talking about is about the Mercury, about the orbit of Mercury, which doesn't go like the left-hand figure on that slide, as you might imagine if you don't know about Mercury. It actually goes more like the right-hand side picture. In other words, it doesn't keep going round on the same ellipse, but the orientation of the ellipse itself actually shifts around. Now, that was well known by observational astronomers for a long time. Newtonian theory and other attempted theories tried to explain this fact, and none of the theories could give a satisfactory explanation. And then comes along Einstein and says, my theory takes care of this. So Brush says this is a lot more impressive than just randomly predicting something that nobody had thought about before. So I think that also makes a lot of sense. Where does all of that leave us? When I teach this topic to my students, I leave the question unresolved so that they can arrive at their own answers. Well, that's what I tell them. And it is true. But another part of the truth is that I've never had a definite answer to give them, even if I wanted to, until now. In the course of preparing for this lecture, I considered this issue all over again and have arrived at an answer that I think is fairly satisfactory, at least to myself. I think the first thing to say is that the confirmation of theory by empirical evidence is a complicated business, and there are many factors that affect the goodness of evidence. The novelty of prediction is just one of those many factors. Here it is very helpful to review the sensible introductory overview that Carl Hempel gave of the empirical confirmation of scientific theories in his introductory textbook of philosophy of science. Hempel lists many of what he calls criteria of confirmation and acceptability. And being confirmed by novel predictions occurs as just one of 6 such criteria. But I would take this one step further than Hempel and say that the criterion of novelty is in fact only secondary. in the sense that its importance only comes from the fact that it can help the satisfaction of another criterion, namely what's listed second on that list, the variety of evidence. I agree with the logicist argument that the novelty of prediction in itself has no special value in the confirmation of theories. But novelty is valuable because it ensures independence. Testing a theory through a novel prediction made by it means that the evidence gathered in the testing process is guaranteed to be different from the evidence that was originally used in inspiring the theory itself. This ensures, if the outcome is positive, that the variety of evidence supporting the theory will have increased. So that is good, but let's put the virtue of novelty in its place. Novel prediction is not the only way to achieve variety of evidence. For one thing, we may make use of facts that were already known, but not considered in the making of the theory in question. This is a point actually already evident in the statement by Descartes, which I quoted earlier. Earlier I quoted it as an expression of predictionism, but actually it's more subtle. Descartes speaks of phenomena of which we did not previously think. He doesn't say phenomena of which we never knew. We did not previously think, I think he means, when we made up the theory that we're trying to test. So now I think you'll be able to see that this is more properly read as an advocacy for variegated evidence base, and it says nothing about the temporal order in which the evidence and the hypothesis have come into being. Various modern philosophers, such as Alan Musgrave and John Morrell, have consolidated Descartes' insight into the doctrine of what they call use novelty, or the heuristic view of evidence. Without going into details of that discussion, let me just state my view that the point of use novelty too is not novelty as such, but the achievement of evidential variety. This may sound odd, but I have to conclude that foresight is not a virtue in itself. It is a virtue only when it helps achieve other aims, and that is in the context of the scientific method. Now, there's one very interesting example which I would spend some time on if I could, but I must rush through this rather briefly. It's the periodic table of Mendeleev. That's the form you're all familiar with. This is the original form, which you may not have seen. And the key here is the various question marks. And the question marks are exactly where Mendeleev made the famous novel predictions. For example, he said, there would be an element quite similar to silicon, but heavier. And that turns out to be germanium. And he had originally called it Eka silicon. That table gives you a comparison of the predicted and actual properties of germanium. And the agreement is really quite impressive. And there are two other similar cases like this. And these cases of novel prediction are very often touted as what really vindicated Mendeleev's periodic system. But the story is much more complicated. And if you look carefully through this case, it will illustrate quite nicely the general points I'm making. So, for example, this is a list compiled by the philosopher of science Eric Sherry, who has written a whole book about the periodic table, about not just the three great predictions Mendeleev made, but all of the predictions he made of new elements. And you can see that about half of them were never found. Only 3 of them were found at the time. So the picture is quite mixed. And this is the really interesting bit. The crisis Mendeleev had was actually when the so-called noble gases were discovered, the right-hand side column in orange in that picture. And it wouldn't have been such a problem if they had all been discovered at once, but actually it was first argon, then the rest. So when there was just argon and the periodic table was missing that whole column, Mendeleev had no idea where to fit that new element. And he was forced to speculate that argon was actually not an element, but a weird form of nitrogen, N3, which fitted the atomic weight roughly well. So this was a major crisis of accommodation of facts discovered independently of his theory, and the fact that he was eventually able to accommodate in a wonderfully nice and neat systematic way all of the noble gases on that far right column was actually a great vindication of his system. So you can see that evidential support for Mendeleev's theory came from all kinds of directions, and it was not a straightforward story as either the logicist or the predictionist would have it. Now, at this point, let me pull back to the original overall plan of this lecture. So I give you again the slide of 4 questions I asked, and now we're on the third one. Can we foretell the future of science? So far, I've addressed the first 2 questions and concluded that modern science is indeed very successful at making novel predictions, but that this acknowledged ability is only as valuable as its ability to organize and explain phenomena discovered in other ways. So what about the next question, which concerns, I would say, foresight about science rather than foresight in science, right? Can we foretell the future of science itself? And I'm going to argue that scientists and others have been very unsuccessful in predicting the course of the development of science itself. Many eminent scientists have got this badly wrong. It has even been said that science fiction writers are better than scientists themselves in predicting technological futures. And even their interesting predictive success has been limited to technology, in my view, not to the theoretical aspects of science. I don't know if this issue was discussed in last week's very interesting sounding lecture. Perhaps the best known and most embarrassing variety of foresight failure by scientists is various predictions of the so-called end of science. For example, various physicists of the late Victorian era are known to have stated that all the important things had been discovered already in physics and only the details were left to be worked out. The acute irony is that they made these statements just on the eve of the great upheavals brought by the advent of relativity and quantum mechanics. One of these unfortunate physicists was American experimentalist Albert Michelson, who would bring the first ever Nobel Prize to the United States in 1907 for his work on precision experiments in optics. At the dedication of the new Ryerson Physical Lab at the University of Chicago, which he designed and later directed in 1894, he said, "The more important fundamental laws and facts of physical science have all been discovered, and these are now so firmly established that the possibility of their ever being supplanted in consequence of new discoveries is exceedingly remote. Our future discoveries must be looked for in the 6th place of decimals," which is what he was good at. Aside from the timing of this remark, there's an additional layer of irony in Michelson's statement. He was the Michelson of the Michelson-Morley experiment, which was the best attempt up to that point to measure the speed of light in different directions, from which the velocity of the Earth's motion with respect to the ether could be inferred. Now, Michelson and Morley's results kept returning no difference between the speed of light in all directions, which greatly puzzled many a physicist. And eventually Einstein would come along and say, let's then just get rid of the ether, and let's postulate that the speed of light is the same in all directions. That's his famous light postulate at the basis of special relativity. So Michelson, having brought about the revolution of relativity in a way, was at the same time predicting that no such revolution would ever happen again. And it's not clear that Michelson ever agreed with Einstein's theoretical views. So it may be that he was consistent in his view that Classical physics was done, and he was not going to change it. Now, there's also an interesting story about Lord Kelvin, which I can also tell you about privately. Sorry, I will tell you if you're groaning. This is a subtler but equally interesting case of William Thomson, better known as Lord Kelvin, the Cambridge-educated professor of natural philosophy at Glasgow. Kelvin said, "The beauty and clearness of the dynamical theory, which asserts heat and light to be modes of motion, is at present obscured by two clouds," by which he meant the problem about how to understand the movement of bodies through the ether and the problem of black body radiation. Now, Kelvin thought of these clouds as remaining anomalies to be resolved before the system of classical physics could be tidied up and completely established. Instead, they turned out to be major instigators of the upheaval that overthrew classical physics completely. The first cloud leading to relativity, the second cloud to Planck's quantum mechanics. At least Kelvin did notice that these clouds were there and not going away easily. But who can tell for sure what clouds will move away or dissipate, and what clouds will bring us a thunderstorm? That is just my point. Now, I do not cite such cases in order to denounce the particular physicist involved for failures of judgment. I would actually say that their judgments were in general as good as anyone else's. Rather, what the two cases illustrate is a general phenomenon. It is extremely difficult to predict the future course of scientific development. There's one particular feature which has been worrying to philosophers of science, namely the fact that the very successful theories of science are very often rejected by later scientists as false. Philosopher of science Larry Loudon has turned this observation into a famous skeptical doctrine, which we now refer to as the pessimistic induction, or meta-induction, from the history of science, which is one of the standard arguments presented against scientific realism. And here I've given you a nice, concise formulation of the pessimistic induction due to Statis Psillos, which says, the history of science is full of theories which at different times and for long periods had been empirically successful, and yet were shown to be false in the deep structure claims they made about the world. Therefore, by a simple meta-induction on scientific theories, our current successful theories are likely to be false. Therefore, the empirical success of a theory provides no warrant for the claim that the theory is even approximately true. The pessimistic induction implies that looking at what is successful in today's science will give us no reliable clue as to what will continue to be accepted in tomorrow's science. Loudon gave a long list of examples, ranging from the humoral theory of medicine to 19th century ether theories. Now, one might argue that many of his examples were not all that successful. Against that argument, I've spent much of my life as a historian of science in demonstrating the cogency and power, even predictive success, of some of the long-discarded scientific theories, such as the caloric theory of heat and the infamous phlogiston theory. But the point I want to make today can be made with other examples that will be much more immediately palatable to you. Let's just take two of the acknowledged greats of Cambridge science, Maxwell and Newton. I'm sorry to leave Darwin out, but he just doesn't fit this as well. Newton's mechanics and Maxwell's electrodynamics were probably the two most successful scientific theories ever before the 20th century. But they are now said to have been based on some fundamental falsities, and they have been superseded by 20th century theories such as relativity, quantum electrodynamics, and beyond. Can we not very easily imagine a not-so-distant future in which the superstring theories and the Big Bang theory are rejected as once successful yet false theories? Now, it is often argued that something like Newtonian mechanics isn't all that false. It's just approximately true, and we can see that from the more advanced theories that we now have. To that argument, Thomas Kuhn famously responded that yes, that is true at the level of numerical formulas, but at the level of the deep ontological claims it made about the nature of the universe, it is entirely wrong if we now believe our modern theories. So Newtonian theory was based on the idea of absolute space and time, immutable mass, etc., all of which relativity theory has rejected, and quantum theory has rejected a bunch of other things. Now, looking forward rather than backward in time, we can note that the same kind of problem of lack of foresight about the course of development of science. Kyle Stanford, contemporary philosopher, one of my favorite scholars in the field, makes a persuasive historical philosophical case for what he calls the problem of unconceived alternatives. Stanford notes that scientists are often defeated in their attempt to find a true theory by choosing the best one from all the different possible theories, because their imagination is understandably limited and they're not able to conceive of what is later shown to be the right theory. The philosophical point Stanford makes is simple and convincing. Choosing the best available explanation gives no guarantee of the truth of the chosen explanation, unless we know that all possible explanations are included in that available list. And that is precisely what the problem of unconceived alternatives prevents. Stanford gives detailed examples drawn from the history of biology, which I would recommend highly for everyone. For now, I will give you a very simple and brief illustration from more recent science. Most of the scientists trying to ascertain the cause of bovine spongiform encephalopathy, BSC, or mad cow disease, were still tied to the idea that carriers of infectious diseases were all living organisms containing DNA or RNA, including bacteria, viruses, and others. But no one until recently conceived what is the more or less accepted theory of BSC now, namely that prions, which are misshapen proteins that can duplicate themselves, are responsible for BSC and other related diseases. So anyone trying to foretell the future of BSC science back then would have got that badly wrong. And we cannot blame them. We can say very similar things in relation to almost any other major development in science. Would 19th century physicists have been able to imagine non-Euclidean curved space-time? Would cosmologists 50 years ago have been able to imagine dark matter and dark energy, which are now supposed to make up a clear majority of substance in the universe? Without being able to conceive of such things, what predictions would they have made about the future of our knowledge of the most fundamental aspects of the universe? So now, what can we say about the future of science? One short answer is that we don't know. We don't know what will remain stable and what will be overturned. One important feature of that answer is that certainty, especially fanatical certainty on the part of the scientists who believe a given theory, does not seem to correlate with its longevity, not to mention its truth. And it seems that the most fundamental parts of theoretical science are what seem the least stable in the long run. Some phenomenological laws have stayed good for many, many centuries, such as Snell's law of refraction or Archimedes' law of the lever, just to pull out two very familiar examples. It is difficult, I think, to imagine such lasting power in anything to do with our notions of the fundamental nature of space, time, and matter. Similar kinds of observations have motivated so-called structural realists these days, who argue that mathematical formulas stay in science, but ontologies come and go. But if we take a bigger picture view, it's not clear to me that this trend will be stable either. Might we not somehow settle onto a firmly entrenched and well-grounded ontology at some point, While some fundamental change will deeply affect various observations and phenomenological laws based on these observations, or affect the very way we express our scientific observations and theories so that they're not mathematical in our normal sense. These are questions with no obvious answers. And that makes sense to me. We have only been doing science roughly as we know it for about 400 years, or less. How can we be sure that the trends we have seen so far in science will be a good basis for predicting its indefinite future? Science is still young. It would be a dangerous fallacy to project forward the trends we have observed in the first 5 years of a child's life onto the rest of her life, especially if we have no idea how long that life is expected to be. Trying to peer into the future of science, since that's what I'm kind of supposed to do today, I actually see two drastic visions. One is that of an indefinite series of metamorphoses, each stage in it so fantastic that it is unimaginable to those stuck in the previous stage. We have often had this sort of changes in science and technology. Who knows how many more such changes are left? The other drastic vision is less exhausting, but more sobering to contemplate. Science may hit an unexpected dead end, with no further major discoveries forthcoming. The ground of this vision is not the self-satisfaction enjoyed by Michelson or Kelvin. No, I am imagining a future in which humanity has done all the science that we can do within our ability, and we're simply stuck in that state, knowing that there is a lot more to learn, but unable to learn it. It's an unglorious vision, comparable to imagining centuries of future Olympic Games in which no future Usain Bolt is able to run 100 meters in less than 8.5 seconds. If I were forced to make a prediction, I would have to say that I think the actual future of science would lie somewhere between my two drastic visions, or rather, probably a messy mixture of the two. Having given you a sense of the uncertainty about the future of science that I suffer from, I would like to close by considering some implications of that uncertainty, assuming that you accept at least some aspect or some degree of that uncertainty that I've expressed. I started out by separating out questions of foresight in science from foresight about science. Now, in closing, I must note that the two questions are really not entirely separable. The uncertainty about the staying power of scientific theories, even predictively successful ones, actually raises a serious question about the value of predictive success. There are two aspects to this. First, predictively successful theories may end up being rejected for various other reasons, as we've seen in the pessimistic induction argument. Contrary to Lakatos and others, predictive success is not the be-all and end-all of science and its progress. Secondly, predictive success itself may not last. Even for theory that make a string of successful novel predictions for some time, its predictive success may dry up. In fact, in the Popperian, Lakatosian, and Kuhnian pictures of scientific progress, this is almost taken for granted. Otherwise, why would scientists go over to new theories, research programs, or paradigms? A less imaginable but possible scenario is that the predictions we used to make successfully, or the predictive methods we used to employ successfully, would somehow cease to work. This would happen if nature itself changed in relevant ways. In any case, a lack of foresight about science ultimately limits foresight in science. And limited foresight in science, in turn, significantly reduces the promise of any real foresight about the development of science. Because if we want to foretell the future of science, what method would we have for that, other than some sort of science itself? So all these thoughts make clear that predictive success enjoyed by science cannot provide a sure guide to the future of science or to the future that science seems momentarily successful in foretelling. The future remains uncertain. You knew that already, long before you walked into this lecture, so I haven't told you anything new. The remaining question is also the obvious one. How do we prepare for an uncertain future? At one level, we can only continue to live on the basis of the regularities that we do have, that have not failed us yet, while being aware that these regularities may fail at some point. This is a humble lesson that has been voiced by a range of great thinkers, including Isaac Newton and David Hume. At another level, we can prepare ourselves for uncertain futures by maintaining flexibility and readiness for surprises. At the societal level, such flexibility comes mainly from the cultivation of pluralism, according to which different people pursue different ways of doing things, so that hopefully, when surprises hit our society, somebody somewhere is ready to propose a nice solution. About pluralism, I have spoken on other occasions, and there will be other occasions yet to speak about pluralism, so that's not what I'm trying to sell today. The theme I want to emphasize today is not so much pluralism as humility, though the two go very closely together, and that is my final theme. Epistemic humility allows a view of allows a view of the future of science and its present that avoids both of the dyspeptic visions that I outlined earlier. This vision is not original to me, but due to Joseph Priestley, the 18th century chemist, theologian, and political philosopher. Priestley had this very appealing picture of how the development of science goes. He says in one of his books of pneumatic chemistry, "The greater is the circle of light, the greater is the boundary of the darkness by which it is confined." So I've drawn a picture myself to illustrate that. So knowledge for Priestley is this little circle of light in a vast darkness of ignorance. I will come to correct that statement I just made in a subtle way in just a moment. But Priestley said, when this knowledge grows, the circle gets bigger, but so does its circumference, which is really what ignorance is. The vast darkness is not even ignorance. It's just stuff we don't know. I hope that doesn't remind you too much of Donald Rumsfeld. For Priestley, the operative kind of ignorance that we deal with in science is at the periphery of knowledge. The questions that we know how to ask because we know the stuff that's in the circle, but we don't know the answers to. And some people may find this a depressing picture, because the more we know, the more we realize we don't know. But for Priestley, it was just the opposite. And here's what he goes on to say in that passage I quoted. He says, "But notwithstanding this, the more light we get, the more thankful we ought to be. For by this means we have the greater range for satisfactory contemplation. In time, the bounds of light will be still farther extended, and from the infinity of the divine nature and the divine works, we may promise ourselves an endless progress in our investigation of them, a prospect truly sublime and glorious." Now, for Priestley, who was a devout Christian, this all had to do with the infinity of divine nature. Personally, I'm not a Christian. I'm not particularly religious in any way, but I think we can take Priestley's lesson simply on the basis of human humility. Through his humility about human epistemic capability in comparison to the apparent inexhaustibility of the universe, Priestley was able to accept the uncertainty regarding the content of future discoveries, yet assure himself that future discoveries would continue indefinitely. Seeing the frontier of research as the boundary between a modest yet growing circle of light and an indefinitely vast darkness, Priestley was able to conceive of an unlimited expansion of knowledge in various directions that were unpredictable, yet delightful precisely for their unpredictability. Generalizing Priestley's vision further, I would submit that in a world of insurmountable uncertainty, true foresight consists in recognizing the proper limit of our foresight. Thank you very much. Thank you.
So thank you very, very much indeed, Hasok. That was an absolutely fascinating lecture. I've got a huge amount to go away and think about and read, especially about the history of science, and try and lessen my ignorance. I think you've certainly shown that physicist Richard Feynman's comment when he said, philosophy of science is about as useful to scientists as ornithology is to birds. That's completely not true, but probably we could say that anyway, because at the most basic level, without ornithologists, golden eagles or albatrosses or perhaps kiwis would likely just be extinct anyway. To learn that science fiction is better at predicting the future of science or technology than scientists puts those of us who are scientists very firmly in our place. We're pretty insignificant. And to learn that really the philosophy of science is something that as scientists we should take seriously and attempt to try to get our minds around, even though it's not the easier things perhaps as many of us find, equations and so on are, that's straightforward. Or working on a lab bench is straightforward. We can do that. And philosophy is maybe rather abstract and hard to grasp. We need to try hard. So you've given us all here, I'm sure, a really great deal to think about. And you've covered such a wide breadth of human history and enterprise. Just thank you very much indeed.